There we go. All right. So I think we are streaming already. Let me just double check. Yep, we are streaming. The audio is good, so we are ready to roll. In the previous class, we started to talk about automated theorem proving, which is basically the idea why it is important to study propositional logic, which is something that has been around since 300 BC. Well, some good stuff, is never too much to study, right? But what the reason why we include it into cisp440 instead of a philosophy or math class is it has direct application to computer science. Automated theorem proving is what allows a computer system to look at a program, look at the desirable outcome of the program, and prove once and for all that the program either does it or doesn't do it. Okay, so instead of throwing test cases, hoping that we catch all of the bugs, using the test cases, now it is actually mathematically concluding that the system is going to work correctly, or no, it is not going to work correctly. So that is the reason why we are getting into propositional logic, and also later on predicate logic. So this is the introduction, or this is the first topic that we need to look into. All right, so getting back into propositional logic. So I just reestablished, what tree we are looking at in the forest, and now we're going to go back into looking at some of the pine needles. All right, so so in this particular example, we are defining those terms, or the four tuple of propositional logic to deal with the logic system that we normally deal with. And in this case, we have the constants. The constants are 0 for false, 1 for true. I mean, you can use F and T if you want to, okay? But basically it's the same thing. Omega 1, with a subscript 1 means, these are the operators that only require one single operand. The negation or logical negation operator is the only thing that requires only one single operand. Everything else requires two, so that's why omega 1, which is a subset of omega, only has one single element, which is a logical negation. And then we have omega 2, okay? Omega 2 in this case is a very simple system. It only has and or, okay? And these two are in omega 2 because they both require two operands. And then we have variables. Now variables are really just basically allocating certain letters in the alphabet and say that every time we encounter P, Q, R, S, T, it is a variable. A variable means it is a letter that is representing a value that can either be true or false. Okay? So in that sense, it is the same concept as a variable that you know in programming. In other words, we don't really know whether P is true or not. Okay? It's a container. It can contain either of those values. And then we have something that's stranger. It's called a schemata. So a schemata are symbols that are typically using lowercase Greek letters. So in this case, we have psi, phi, and rho. And sometimes we have more, sometimes we have less. But they're usually in Greek letters. They're a little bit special. So we'll get to schematas a little bit later and find out why they are useful. Basically, variables can only be containing the true or the false value, but a schemata can contain an entire expression. So that's the main difference between a variable, which is using the English alphabet, versus a schemata, which is using the letters of the Greek alphabet. Is that okay? Yep, go ahead. Huh? Which portion? The schematas can contain well-formed formulae or entire expressions, which gives us the ability to look at the structure of an expression. All right. So in order to express 0 is false, not false is true, these things are in iota. So we want to include not 0 or not false, which is an expression known to be true in iota. Remember what iota has? Iota has a whole bunch of well-formed formulae But what is so special about the well-formed formulae that we put into iota? Well, all well-formed formulae, because they're called well-formed, they're syntactically correct. But there are reasons why we have several of those things inside the set of iota. Yes? Those are the axioms. Yes, those are known to be true, given to be true. Do not question why they are true. So they are the starting points of the derivations. Okay, so that's why the set of iota is so important, because it's the starting point of the entire system. Now we can also contain other things that are known to true. Known to be true, true and true is known to be true. Um, true or true is known to be true. True or false is known to be true. False or true is also known to be true. So all of these expressions are also automatically put into the iota set, because these are the expressions that we know to be true. In other words, we are defining the operators by putting these specific expressions into iota. Because otherwise, the conjunction symbol or the disjunction symbol, they're no more than just a symbol. Okay, they have no meaning whatsoever. The iota is what is giving meanings to the operators. Same thing for the negation symbol. See the negation symbol here, it has no particular meaning until we say the negation of false is true. Then it has meaning. The symbol for true, which is 1, also has no meaning until we put it into iota. So iota is particularly important because it forms the foundation of everything else that we can possibly prove in this particular system. So are we okay with that? Do we understand what things go into the iota and what is the significance of those things that we put into the iota set? Okay. So given that, now we move on to zeta, which is the set of all the quote-unquote transformation rules, which are also called productions. So a production looks like this. It looks like there's a set on the left-hand side. There's a little t symbol that is kind of rotated counterclockwise by 90 degrees. And then there's an expression on the right-hand side. And you can see that we are not using PQRST anymore. We are using Greek letters. Okay, so tell me again, what are the Greek letters? What is the special name that we give to the Greek letters? Schemata. Okay, very good. So the reason why we use schemata is because these are placeholders for well-formed formulae. Okay, what it is saying is, if you can find a well-formed formula psi that is known to be true, and if you can find another well-formed formula, this is psi, this is phi, that is also known to be true, okay? Then those two things that are known to be true is enough to, quote-unquote, infer, okay? That's the inference symbol, to infer that psi and phi as a conjunction expression is also true. Is that okay? It's inference, not implication, okay? And there's a major difference between those two concepts, but right now we'll just say that this is inferring, okay? So what can we use in the iota, for this purpose? Well, we know not zero is true, okay? That's given. We know true itself is true. So now we know, not false and true is also true. Okay, kind of trivial, but that's how we build up additional well-formed formulae that are also known to be true. Remember the analogy that I used in the previous class? You have an infinitely large space of well-formed formulae. Okay, there's a whole bunch of stuff that are all syntactically correct. But which ones are true? Because we're only interested in the ones that are actually true. So this is how you can, quote-unquote, propagate the labeling of, oh, this is true. Oh, by the way, that is true too. Oh, by the way, that is also true. This is how we can propagate the labeling of which well-formed formula is actually true. This is one of the inference rules. There are many other inference rules depending on how complete you want your propositional logic system to be. Now, there are also productions that are kind of funky, okay? Look at this one. It's an empty set. So the empty set is basically saying, I don't need to know anything at all, okay? And then I can infer right away any well-formed formula or the negation of that well-formed formula is known to be true. Isn't that cool? In other words, without knowing what the value of, let's say, the variable p is, okay, I can now suddenly say p by itself is a well-formed formula, not p is also a well-formed formula. Well, they're negations of each other, so now I can say p or not p is true, which is definitely true, but is it useful? Nah, probably not very useful, but it's true. Is that okay? So some well-formed formulae can be labeled true without even knowing what is known to be true. We can just start to label those things as true. Most of those are not really particularly useful, but the system does has to specify that because this is capturing what the symbol or is actually meaning in normal logic. So are we doing okay so far with this understanding? I think I skipped a little bit of what is a well-formed formula. So let's go back to the well-formed formula. To explain well-formed formula, let me start my tablet here. Okay, so to explain what is a well-formed formula, it is somewhat recursive. Okay, so the first thing that applies is if a particular thing, okay, I'll call this x, okay, if x is an element of alpha, this is the alpha set, it implies x is, okay, a well-formed formula. So you take anything out of the alpha set, okay, which basically is the alphabet of the propositional logic system, that by itself is guaranteed to be well-formed. So in our example, 0 is well-formed, 1 is well-formed, P, Q, R, S, T, psi, phi, rho, those things all by themselves, they're all well-formed, no problem. Okay, then what else? Well, then we say, if you pick anything, if you pick an operator from, say, omega 2, okay, that means W1, okay, and W1 is a well-formed formula, and W2 is a well-formed formula. When you have this conjunction being true, it implies W1, whatever operator you choose, W2, is also well-formed. So this is the recursive part that makes it possible to label complex expressions to be well-formed. This is the recording mic too, so we might have a little interruption in the recording. Thank you. So is that okay? So if you say, okay, if P is well-formed, okay, because P is well-formed, it's easy, it's there. Q is well-formed because it's also in alpha, and then we pick conjunction as an operator from omega 2, which are basically all the operators that require two operands. Then we say, oh, then P and Q is also well-formed. So that's how we define things that are syntactically correct. Is that okay? Now, for the same reason, you can say, if I choose an operator in omega 1, and then W1 is well-formed, then we can say, OP W1 is also well-formed. That only applies to the negation operator, because that's the only unary operator that we have. Is that okay? So the idea is, it's not any different from how you would think of a general expression as syntactically correct. Is that okay? All right, so with this out of the way, we can get back to the notes. And then we have things that are kind of interesting. So we have things that are like this. That, by the way, is De Morgan's law. So De Morgan's law says, I only need one thing that is known to be true, because this is the set of things that I need to be known to be true in order for the inference to work. So I need something like this. It has to be the negation on the outside of a disjunction of a disjunction, and then we have two sub-expressions. One is phi and the other one is psi. Okay, if you can give me a well-formed formula like this that is known to be true, then I can give you a conclusion. I can infer that this expression is also true. This is a conjunction. It's not a typo. And then we apply the negation to the individual components of the disjunction. It's known as De Morgan's law. So we're still doing okay so far with this particular inference. Okay, so this is why schematas are useful, because what if phi is not just p, q, r, s, t? It's nothing simple. In fact, phi and psi each is a 6-line long expression. It's a well-formed formula. Doesn't matter. Okay, it's a placeholder. Put whatever is here into here. Put whatever is here into here. The inference still works. Is that okay? Yes? Okay. So that's why the schematas are useful, because it can be used to express inferences like that. What about this one here? This one is saying if you know two logical negations are true, okay? The negation of phi is known to be true. Don't ask me why. The negation of psi is also known to be true. Now remember, phi and psi are placeholders. Each one can be a really simple expression, can be 0, can be 1, can be just p or q or r and so on. But each one can also be a really long, complex expression on its own. I'm just saying that the negation of some well-formed formula and the negation of some other well-formed formula, they can be the same too, infers the negation of the first placeholder or the second placeholder. The negation of the overall disjunction is also going to be true. So this is how we express, how we can propagate the labeling of well-formed formulae that are true. Is that okay? And you can see how this can yield a lot of labeling of well-formed formulae that are true, but it's not productive whatsoever. You see how we can kind of keep on going and going? Because just this thing by itself can generate an infinite number of well-formed formulae, and they're all labeled to be true. Not particularly helpful, but they're all correct inferences. Okay. So let's move down a little bit. Let's scroll down a little bit here. Okay, so we have an example here of a logic system and what we can put into iota in addition to the usual axiomatic things. So we can put these things into iota. Okay, so just to give things a little bit more meaning and also to make it a little bit more fun, we can now say that p as a variable is equivalent to the statement of tech is boring. Tech is boring is a statement. It is a variable as well, because it can be true, it can also be false. Okay, and that's why it's called a variable. It can be either one. I'm just labeling. Okay, I'm just using a label to label p. We'll label q as another statement that can be true or false. Have the class falls asleep in cisp440. It's a variable. It may be true, may be false. Is that okay? We got r. Okay, r is also a variable. And the meaning of R is many students feel rejuvenated after cisp440, presumably because they fell asleep. Okay, so now we have three variables, P, Q, and R. Is that okay? So iota doesn't have to say that, oh, P is known to be true, or R is known to be true, or Q is known to be true. Iota can basically contain expressions like this. Not P or Q, which means it is a known fact that tag is not boring or half the class falls asleep in cisp440 is known to be true. Well, but does that really tell you, about the P and the Q, which one is actually true, which one is actually false? No, it does not. Okay, it simply means that the negation of P or Q is true. How do you make that true? There are several ways to make it true. We don't know which way. Is that okay? And then the next one is, let's also say that not Q or R is also known to be true. So in the context of this, joke here, it means not Q means Q is right here. So not Q means half the class, half of the class does not fall asleep in cisp440. Okay, and and then we have an OR with R, and R is many students feel rejuvenated after cisp440. So once again, we know the expression is known to be true, but we don't know what the truthfulness of each individual variable. Is that okay? So now the question is, knowing that these two expressions, not P or Q, not Q or R, are actually known to be true, along with other things in the iota, the other axiomatic necessary things in iota, what can we prove? Can we prove this? Can we prove from these two expressions, can we prove not P or R is also guaranteed to be true? That's the question. And we want this to be automated. In other words, we punch in all the axiomatic truths, we add in all the interpreted truths about the world, and then we ask the computer, can we know this is also true? Because if we can do something like that in general, then we'll be on our way to automated theorem proving for programs, which is very, very helpful. So do we have any questions about this example at this point? Yep.
Talking about Q,
Mm-hmm.
not Q and Q are equal.
Not exactly.
When you're talking about a particular half of a class, we can mean another particular.
Well, I misspoke when I said half the class does not fall asleep, because this says half the class falls asleep in cisp440. So the negation of that is not. It is not the case that half the class falls asleep in cisp440, which means there are many, many scenarios that will meet the negation. Nobody fell asleep in text class. Well, that meets the requirement of the negation. The entire class fell asleep. That also meets the requirement. Okay, almost half the class meets the requirement as well, or just a little bit more than half a class also meets that requirement. In fact, half the class is a very rare occurrence because with a class of 40, you need 20/20 to meet that requirement. If I have an odd number of people in this class, then I will never meet that requirement, technically. Yep. If the class is empty, that is a good question. If the class is empty, can we say half the class falls asleep in the class? Well, because half of 0 is 0. Yep. So it would still meet that requirement, by that definition. Because half of nothing is nothing, but it doesn't preclude that the class itself is empty. So having 0 students falling asleep in a class of 0, it's still meeting the requirement of half the class is falling asleep. But it's also fitting the requirement of half the class is not falling asleep. Yep, so that's a very interesting special case. All right. So the next section here talks about completeness and soundness. So to establish these, okay. So to establish whether something is complete, we're going to have to rely on some extra symbols. So let's say we are looking at one particular inference, okay, just to be very specific. This particular inference is going to say phi 1 all the way up to phi n, so there are n individual well-formed formulae that I need to be true, that I need to know to be true, infers psi. Okay, so that's what the rule is saying. Then we basically say in this case, with this particular inference, we basically say that the set of all of these phi well-formed formulae syntactically entails psi. That's just a name, okay? It's just it's just a name. Semantic entailment, on the other hand, is expressed as that. It means that using conventional Boolean algebra, we can actually prove that the conjunction of all of these phi's implies psi. Okay, so what is the difference? This is a syntactic operation. Okay, we are just syntactically going through the operation and move the symbols from here to here, move the symbols from here to here, move the symbols from here to here, and then use the operators as it is formatted in psi. Okay, so nobody is asking about the meaning of anything. We are just doing syntactical operations. This, on the other hand, is using the actual meaning of the conjunction operator and see whether that is see whether that's implying psi. So one is syntactic, the other one is semantic. Okay, do we have any questions about what is syntactic versus what is semantic? What can change the semantic so that I actually have a mismatch between these two? If I specify the rules incorrectly, that's one, okay? But if I have the wrong items in the iota, I can also end up with a mismatch between what can be derived syntactically as opposed to what can be derived actually mathematically. Is that okay? So there are two things of concern here. Okay, the other way to look at this is what the computer would do. This, on the other hand, is what you would do. Okay, because you look at the meaning of statements in a mathematical proof. So you go by the meaning when you do the derivation. The computer, on the other hand, doesn't understand the meaning of anything. The computer is only going for the syntactic transformation because that's the one thing that it can do really, really well. So the question now is, if you can prove something, can the computer prove the same thing? The second thing that we need to ask is, if the computer can prove something to be true, is it actually true? So we need those two to be matching in order to say the system is useful. So for completeness, it basically means for each logical derivation using Boolean algebra. So if you can derive it by hand, okay, it also means that it can be done syntactically. That's completeness. And then soundness is the other way around. Soundness is basically saying that if it can be derived by the system, you can also do it by hand. Is that okay? So let me say that one more time at the tree level, at the pine tree level. What is highlighted right now, on the screen, is saying if the computer can prove something to be true, you should be able to prove it by hand as well that it is true. And that part is soundness. The transformations or the inference are sound. Now, just being sound is not enough because it may not be complete. There are certain things that you can do, but the computer cannot do. Okay? So that's why we also need completeness, because what completeness is implying is this statement here. Let me highlight that. This part means if you can prove something by hand, the computer should be able to do it as well. And one does not imply the other one, and we want both in order for a propositional logic system to be useful. So are we doing okay so far with these terms? Okay. So we are basically done with classical propositional logic at this point. Some other classes may include more details in propositional logic, but I'm just going to stop here because classical propositional system is not very useful, and I think last time we talked about that already. Okay, so you can kind of imagine that you have an infinitely large haystack. Okay, remember that analogy? So that haystack is representing every syntactically correct formula, or otherwise known as well-formed formula. The needle is the statement that I need to prove. Okay? So now the question is the needle even in a haystack? We don't know. We really do not know whether the needle is actually true or not, whether it is in the haystack or not. And we know it's syntactically correct, okay? But is it actually in the haystack? That we do not know, okay? So that becomes a problem because you have an infinitely large space, and you don't even know whether what you're looking for is in that space or not. So it's not like you already know this is known to be true. Yes, I know it's in the haystack. So it's just a matter of time to search and find it. Okay, we don't even know whether it is true or not, which means you can spend your computer can spend 10 years working on that problem. It cannot yet prove the theorem. It doesn't mean the theorem is not true. It can also mean that it just has not found a way to connect to that particular expression. And there's no way for you to differentiate between the two. Is it not done, or is the theorem cannot be proven? Okay. So that's a problem. Okay, that's a problem. So what we need to do now is to say, okay, we need something a little bit more deterministic. In other words, we need something that has a known termination time. Okay, so that we can say conclusively, yep, that's a theorem, or nope, that is not a theorem. We need to know for sure which way it is. Okay, so that's the reason why we are moving on to talk about resolution. Resolution depends on this weird proof. Okay, now we know this is a proof because in the end it is true. It is basically saying this statement is always true regardless of what phi, psi, or rho are. This statement is always true. This implication is always true, which is kind of cool because it means every time you see something like this on the left-hand side of the implication, you can simplify it to the form on the right-hand side. Is that okay? So you can look at it as a simplification kind of thing, because you start off with what, 3 schematas, and you end up with only 2. Okay? So that means you can start out with a huge, long, big, complex expression, and using these steps, you can kind of make the expressions smaller and smaller and smaller and smaller until hopefully we can get to something that is a contradiction. So we'll defer the discussion of proof by contradiction at this point. We'll focus on this proof, okay? So what do you think about this proof? Let's do it line by line, okay? Because when you look at the whole thing, it's go like, there's no way I can actually understand this proof. But when you go line by line, okay, it shouldn't be that difficult. So we'll go line by line and see what's happening. So what happens when I look at this side and end up with this side here? What operation did I perform, or what did I remove? Yep. The implication is gone, okay? Well, but it's not exactly gone. It is just presented in a different form. Because A implies B means not A or B. That is the definition of implication. And I just used the definition of implication to remove that operator and replace it with a negation of the left-hand side, and then an or, and then the left, and then the right-hand side. That's all I did, okay? So that means, by now, you probably should know about the definition of implication. Okay, that's a very crucial thing for you to know is, A implies B. It's really just not A or B. Okay, so first line is done. what did I do between line 1 and line 2 here? What is different? Well, I actually did several steps, but let's look at the first step first. See how this and is gone and instead we have an or here? What happened? I applied De Morgan's law. Okay, De Morgan's law is applicable because this and is negated by this not. So as a result, I applied De Morgan's law by negating both sides of the and, but then I also have to change the operator from an and to an or. That's what I did, with the first part of the expression. What about the second part? The second part used to look like this, and now it looks like this. What did I do? I got rid of the, yeah. Yep, I got rid of the parentheses because of the associative law. Okay, just like with addition, disjunction also has plays by those rules. So the parentheses, you can order the parentheses in any way when you have a series of disjunctions. It doesn't really matter whether you do this disjunction first and then do the outer disjunction, or whether you group it in a different way. Okay. What about from this row to this row here? What did I do? Looks like I applied De Morgan's law again to the inside expression. So I look at this expression overall and look at it and go like, it is the negation of an or. I can apply De Morgan's law again by negating the individual parts. But then I have to change the disjunction, which is the or, into a conjunction, which is an and. And I'm doing the same thing to this particular sub-expression and turn it into just an and here. And this side has not been changed. All right, from here to here, okay, from the third to the fourth row, what did I do? I did something really stupid. Well, it seems senseless, okay? It's not wrong. It is just like, I don't know where you're going with that, okay? Because I turn phi into phi and true. I turn rho into rho and true. That doesn't change the meaning or the value of the expression. It's just like, why did you do that? Because anything and true is anything. Hold on a second here. How do we know that? How do we know that? Okay, let me focus on that particular question. Okay, so how do we know that, I'll use AB so that we don't confuse these symbols with anything that we are actually saying. So how do we know that, A versus A and true are the same? How do we know that? Does it make sense? Maybe. Well, let's try it in a truth table manner, okay? A is a Boolean variable. It can either be false or true, right? What is false and true for the first row? False and true is false. Very good. True and true is true. Okay, well, the two columns are exactly the same. So that is the proof that I need to establish, whatever is really the same thing as whatever and true. Okay. This is one really, really useful tool to prove two Boolean expressions are the same. You cannot do this to usual algebra, the regular arithmetic algebra. Can't do that because, you cannot enumerate all the possible integer values. But in Boolean algebra, we can do this because there are only two possible values to each variable. So we can just kind of enumerate everything and go like, okay, considering all possible cases, does this expression give me the same result as that expression? If they do, they are exactly the same. And you can use this technique to prove De Morgan's law. Okay, it's pretty much the same thing, except you have 4 rows instead of 2, because instead of just A, you have AB. So you have A and the negation of A and B, the whole thing, as one column, and then you have not A, the whole thing, or not B, the whole thing, as another column. And then you have A, B being the independent variables, so they can be zeros or ones being completely independent. That's why you have 4 rows. And then if you prove those 2 columns being the same, then they're equivalent. How many of you are now having a mental picture of what I just said? That's what I thought. So I'm going to do it here. All right. So we have A and B as independent variables, which means when A is false, B can be false or true. When A is true, B can be false or true. Is that okay? Now we look at the negation of A and B. All right. So if at least one side is false, I know the whole thing is going to be false, but then the negation of the false is true, so we know it is 1, 1, 1. When A and B are both true, then A and B is true, the negation of that is going to be false. Then we have not A, the whole thing, or not B, the whole thing. I claim that these two columns are the same. So if A is false, then not A is true. Well, that means the whole thing is true. Same reason over here. For the third one, A is true, not A is false. But B is false, not B is going to be true. You only need one side to be true for the entire disjunction to be true, so the third row is true as well. For the last row, A and B are both true. Not true is false, so we end up with false or false, which is also false. And you can see how those two columns are exactly the same. This column and this column are exactly the same. So what do we conclude? De Morgan's law. If you see something like this, you can rewrite it like that. Or if you see something like that, you can rewrite it as something like this. Now, De Morgan's law is really fun and also really useful because it is the mechanism that you can use to eliminate a particular operator. If you say I have to express everything using just and, I cannot use or whatsoever, this can help you. The other way around is true as well. Okay, so you can actually use it to eliminate one of the two. Okay, you have to keep one, but you can eliminate the other one with the help of negation. Is that okay? So for those of you who are considering getting into computer engineering or electrical engineering, especially the digital side, this is going to be really, really helpful in your career, in all of your other classes. All right, so getting back to the content on the web, we are moving on. So I ended up with this one now. Okay, this is my new expression. So what did I do here? Well, I look at the one, the true, and I go like, yeah, I know certain things that are true. For instance, psi or not psi is known to be true all the time. Psi or not psi is known to be true all the time. Does it make sense? It makes sense, but can I prove it? Just because it makes sense, it's intuitive, doesn't mean it's true. Can I prove that psi or not psi is always going to be true? And how am I going to prove that? A truth table. Okay? So I'm going to leave that one to you. Okay? I'm going to leave that one to you. What about between these two rows? It's called distribution. It works the same way as arithmetics. So I have psi or, phi. Phi and psi or not psi. Okay, if you look at the conjunction as a multiplication and the disjunction as an addition, it works the same way as in arithmetics. Okay, so I'm really just distributing, so it ends up with phi and not psi, or phi and psi. Is that okay? And the same thing for rho. Basically, it's exactly the same deal. It's just distribution. So are we doing okay so far? Okay, up to here. And then what do? After that, this is the new row, okay? And you can see some extra parentheses, and so what did I do? It's the same thing that you would do in arithmetics. It's factoring, okay? So what I do here is I look at things that contain not psi. This has not psi, okay, and this has not psi as well. So I'm factoring not psi to the outside of a conjunction, and then I'm looking at the other part of each sub-expression. which contains not phi with this one, and it contains phi with the other one. So I factor out the not psi, and then I group the rest into its own expression, which is the same thing that you would do with arithmetic factoring. Is that okay? And I do the same thing with rho. I identify that I have psi and rho here. Psi and rho is psi and rho. Oh, I think I made a mistake somewhere, didn't I? Oh, right here. Oh, yeah, okay. It has. Yep. Yeah, just scroll a little bit more. Yep, there we go. Scroll bar. There. But it's the same mechanism, okay? I use factoring to group the row or not row into its own disjunction. Then I move on to the next row because I can see that, oh, this is a constant of 1. In other words, it's always true. And this is always true as well. So I end up with true and not psi. I also end up with psi and true over here. The rest are pretty much the same. Is that okay? But we also know that true and whatever is just whatever. Okay, we just proved that earlier using a truth table. So I just say, this is just a long way of saying not psi. Okay, not psi is fine. And this is just a long way of saying psi, so put psi here. Okay? But what do we know about psi or not psi? It's always true. Okay, so we have a true here because of that. Well, when you have a true and then the rest are all disjunctions, the whole thing is going to be true. So that's why we got a 1 here. It's a mathematical proof, okay? And there are probably alternative versions to this proof, but this is mine, okay? I actually spent the time to work on this myself, but if you look it up, it probably can look a little bit different. There are different ways to prove it. But the bottom line is what? The bottom line is this implication is always true. It doesn't matter what phi is, doesn't matter what psi is, doesn't matter what rho is. If you see something like this, the thing on the left-hand side of the implication, then the thing on the right-hand side has to be true. Isn't that fun? We got rid of one of the terms, okay? That's the magic of this whole derivation is psi is gone. It was in the original expression, is not there anymore. Nobody seemed to think this is impressive. Yep.
Can you explain the last expression again?
You mean this one?
Yeah, that one.
This one? Okay, so the second to the last row has a true. The true is because of the not psi or psi. So if you group these, it becomes a true. But then true or whatever is always true. Okay, so let's say we're not convinced, right? So what do we do? This is starting to sound like an infomercial. So what do we do? Well, we say, here's a variable, and we are concerned about the variable or true, okay? So the variable itself can vary, which means it can be false or true. So when A is false, what is A or true? True. When A is true, what is true or true? True. Oh, so that means A or true is always true regardless of A. Do you see how I apply this? Because in the notes, you can kind of look at this entire side as the variable. So we have true or blah, 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 okay, which is always true. The very first thing. Are you talking about the inference? I don't think it makes any more sense any further up. function. Okay. Maybe not. Maybe not in the notes. Maybe on my tablet. No, it's in the notes. Okay. So I think if there's anything derived, it has to be here. Which one? That's De Morgan's law. Okay. I think that's all the logical derivations that we have seen so far in this class. Okay, maybe a little bit later. Okay. Um, so we're gonna continue with this. Okay. All right. So this is significant because this derivation here, okay, this implication is called a resolution. Okay, it's the step of resolution. You basically start with something that looks like what it looks like here on the left-hand side of the implication, and you end up with something that's what it looks like on the right-hand side of the implication. And because we know this makes sense, okay, so what we are going to do is we make an inference out of this. Now we are also going to change the rules a little bit here. We basically need to make sure that psi is a single variable. We need to make sure that phi is a disjunction of constants, variables, or negations of variables, and rho is the same thing. And then we can do the inference rule in here. So anytime you can see an expression that looks like this, and you can also see an expression like this, both being known to be true, then we know this expression is also known to be true. The reason why you don't see the conjunction is because if both of these well-formed formula or well-formed formulae are in the set, that means they're true to begin with. So that's why we don't really see the conjunction symbol, because that conjunction is implicit. Okay. So what we'll do now is we are redefining what it means to be a well-formed formula. Okay, so we are just changing the rules a little bit. So the new rules are like this. Omega 1 is still the same thing. Okay, omega 1 is just the negation symbol. Omega 2 this time is just the or. We don't even have the and anymore. We don't need the and when everything in the set on the left-hand side of the infer symbol are known to be true. They are all known to be true, which means the conjunction is implicit. So we don't even need the conjunction symbol anymore. So everything in alpha is basically a disjunction element. Okay, so I use the predicate is ADE to mean is a disjunction element. Okay, it's just a predicate. That's all it is. And then we will also say that the negation of that is also known as an element of a disjunction. So you pick anything out of alpha, we can use it in the disjunction. That's what it means. Is that okay? And then we use this equation here to say, or this, not equation, but this definition, to say that if you have a whole bunch, n, of these components inside the disjunction, so we know that phi 1, phi 2, all the way up to phi n, they're all elements of a disjunction, which means each one is either a constant, the negation of a constant, a variable, or the negation of a variable, okay? Then the disjunction of all of those things is now a well-formed formula. So we are redefining what it means to be a well-formed formula. A well-formed formula is going to be a disjunction. Each term of the disjunction can only be a constant, the negation of a constant, a variable, or the negation of a variable. It cannot be a conjunction expression because we don't even have conjunction as an operator anymore. It cannot be the negation of another or, because that will basically violate the rule of each one is a element of a disjunction. Is that okay? Does everybody understand this rule, how we are changing the meaning of a well-formed formula? I'll give you a few examples to illustrate. All right. So we're going to say alpha contains, P, Q, R, false, true. Okay. The schematas, really should not be used in this case. So that means P by itself is well formed, right? Because this is the simplest disjunction you can have. It has one single term. Okay. P or Q is well formed because P is an element of a disjunction. By definition, Q is the same way. Not P or Q is well formed. Okay. Not P or Q in parentheses is not well formed because now I have a negation of something that is not a constant or a variable. The negation is now applied to the disjunction of something that is not well formed. So let me emphasize that this is not well formed. Is that okay? Is that kind of illustrating, the new rule of what is considered well formed? Okay, all right. So now we have to look into, and say, we now have to look into the quote-unquote completeness of conjunctive normal form, which is CNF. So what that means is, can I look at any logical Boolean expression and convert it into a conjunction of those disjunctions? Okay, so that statement by itself is a little bit confusing, right? So I'll give you an example. There are a few examples down here. This is one, okay? So this is the original expression. The original expression, not only does it have conjunction, it also has implication and all kinds of stuff like that, okay? And it's nested, has levels of operations, so it's definitely not well formed by our new standard. So now the question is, can we convert it into our new standard and turn it into a well-formed formula that means exactly the same thing? Because I don't want to change the meaning, I just need to change its presentation. Is that okay? So we go through this long proof here. Okay, so once again, this is Boolean algebra. What happened between line 1 and line 2? The implication is gone. And how did I get rid of the implication? I used the definition of implication. Okay, A implies B is not A or B. So I look at this and go like, oh, this is R implies Q, and I'm going to change it to not R or Q. Got rid of that operator. Okay. What about between the second row and the third row? What happened between these two? I applied De Morgan's law. There's a negation outside of a disjunction. Apply De Morgan's law. We distribute, quote unquote, distribute the negation into each individual term, but then we have to change the operator from a disjunction to a conjunction. That's De Morgan's law. Is that okay? From the third row to the fourth row is a step of simplification. I look at negation of R and go like, well, that's just R itself, so why say not, right? Okay, so that's what happened here. Between these two, what happened between these two? Distribution. Yep, that's distribution. So you look at R and not Q as one term. I'm distributing that term over P or T. So it becomes R and not Q and P, or R and not Q and T. So that's just distribution. Are we doing okay so far with this? Okay. And then from here to here is also distribution, but basically I'm making a cross product between R and not Q and P, and the other term, the expression is R and not Q and T. So I just make a huge, gigantic mess out of this. There are 9 terms because there are 3 terms on one side, 3 terms on the other side. each term has to match up with every other term, every term on the other side. Does it remind you of Cartesian product? It is. So we got R combined, we got R not Q combined, we got RT combined, and so on. So I made a big mess of 9 terms like that. Okay, it's just really expanded out. Is that okay? And then what do I do from here to here? Distribution, yep. So I took this not P, which is outside of the entire conjunction in the inside, and I distribute it. So needless to say, that makes an even bigger mess, more or less. Okay. And then I do some simplifications. The simplification, if you look at this one, it's like there's no need to say R or R. I mean, R or R is just R. What if you're not convinced that R or R is just R itself? Truth table, exactly. So using a truth table, you can convince yourself easily that R or R can simplify to just R. Okay. Second one, can't really do much about it. Leave it alone. This one, I can't do much about it. Leave it alone. Leave it alone. This one, yeah, we got not Q or not Q, which is simplified to just one single not Q. Okay, let's take a look at the other ones. Gesundheit. I learned to use that in response to sneezes because Gesundheit actually means, I cannot remember. It means something, it's German for, I cannot remember. Okay. I'll remember at some point, just not now. Okay, so with this one, because I can see there's not P or P, that becomes true, so that means the entire expression is true. With this one, same deal, okay, we got P or not P or P, and then the same thing with this one, we have not P or P. So those 3 simplify to true and true and true. True and true and true simplifies to a single true, which is just useless in the conjunction. So now I end up with the second last row here. Yes?
The word is after P, not P, and or not Q or not Q. The next term after it, you kind of skipped it as far as I understood, because as I understood, you said not Q or not Q is just not Q, right? So, and then term after it, you didn't do anything about it.
Which one?
The term after, like this one.
That one?
Yeah.
I didn't do anything. Oh, you mean this one, should still be there somewhere,
Yeah.
but it's lost.
Yeah.
Okay. So let's see. Let me see. I just want to see whether it's actually one of the other ones. Nope, it is not. Okay, so it looks like it's lost, but is it actually lost? Okay. So in order to see whether this is actually lost, we want to find, do we have a term P, not P or P in the whole thing? Yeah, we do. We got this one. So even though I did not explain this one, so good catch over there. So I did not explain it, but this one is simplified out of the whole thing. Now, how can I simplify this out of the entire thing when it is not the same as not P or not Q? We have not P or not Q because of this, which is because of this. Okay, but why can I just get rid of this term here? That's the question. So the question has to do with, is this not P or Q? Does that imply not P or not Q or T? Okay, let me write it out. Okay. So the question is this. Okay, I'll write it on the tablet first, and then I'll present it to you guys. So we have A or B. So I'm not using those terms. I'm just using A or B. And then we have A or B or C. And now the question is A or B implying A or B or C? Okay, so let's switch now. There we go. Okay. So this is the question. I have A or B, I have A or B or C. Now the question is A or B as an expression going to imply A or B or C? Now there are several ways to look at this, and the answer is true, okay? But we can use a truth table again here, okay? So let's go ahead and use a truth table, which means I have to move things a little bit. Let's see. Just cut. Yep. And just move it. Click. Okay, there we go. Okay, so now we have A, B, C. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. So now we have to actually figure out, we have to go ahead and figure out the values. So A or B is going to be false, and then for everything else is going to be true. 2, 3, 4. Okay. And then with C here, we'll only have to deal with only the second row is going to be different, and then everything else is going to be the same, right? Is that okay? So now the question is, what about that implication? The implication itself is true, because the one row that is of any question is this row here. False implies true is true. So how is this useful? I mean, why am I talking about this in a conjunction? So now, so the next question we have to answer is this question. So let me get rid of the implication. Wrong tool. Eraser. There we go. I need a thicker eraser, but this is fun. There we go. Okay. So now the question is, what happens to A or B and A or B or C? Which is the scenario that we have in the proof. Because we got one term that has all three we got one disjunction that has all three terms, and then we have another disjunction that only has two of the three terms. So the question is, can we simplify the disjunction that has three terms out of the conjunction? That becomes the question, right? So what do you think? Let's work it out, okay? False and false is false. False and true is false. And then for everything else, they are all true. Is that making any sense? Okay. So if I focus on this column and this column, do they look the same? They do look the same, which basically means if you see something like this, you can simplify it to just that. Is that explaining it? So that's how I got rid of that term that didn't seem to have a good reason to disappear.
Pretty deep reason to disappear.
Hmm?
That's a pretty deep reason to disappear.
Well, I mean, that's why I like truth table, because with truth table it's a very concrete way of proving, but it's also indisputable. It's not like, oh, it's a hunch or it's just a gut feeling. Nope. We look at all the possible cases. These two are exactly the same. So it's kind of cool in that way. So that is why this term was there, but because we also have this term later on, and that's why this term got simplified out. Okay, very good point. So, but in the end, okay, so if we look at this, this is applying the same rule again, because how did we get from the second last row, which is kind of long and clumsy, to the last row, which is like, wow, that's pretty simple. How did we get rid of a whole bunch of stuff? Well, this one has an extra or R. Get rid of it. This one has an extra or R. Get rid of it. These two are actually the same. And then we look at not P or R. This one has an extra not or not Q. Get rid of that one. So I apply that single simplification to bring it all the way down to just that. So now the question is is this meeting that requirement that we set up earlier? Is it a conjunctive normal form? Well, once again, the conjunction is implicit, okay? So the only expressions left, we only got two expressions to consider. The first expression is not P or R. Is that well formed? Does it meet the requirement that it has to be a disjunction and each term of the disjunction is either a variable or the negation of a variable? Yep. What about this one? Yep, it meets that rule too. So we have just converted something that is somewhat random and involves all kinds of nesting and implication and conjunction to a conjunctive normal form, or a CNF. Is that okay? Yep.
You apply that same idea to the not P or R or T, because the T also disappears.
Because the T disappears because not P or R is already here. So basically what it says is if the overall operation is a conjunction and then you have a disjunction that has more term than the other disjunction, then the one that has more term can be simplified out. Yep. All right. So this is kind of neat. This is an example just to show you that yes, we can transform any Boolean expression of any complexity into a CNF. Now it might take a little bit of steps, it might look a little ugly in between, but we can do it in the end. So here's another exercise, okay, for you guys to do. I mean, you guys can do it. So now the next topic, which doesn't seem to be connected to conjunctive normal form or propositional logic, is proof by contradiction. So I'm trying to lay out these individual pieces first, and then magically all of these pieces will kind of fall in together into the same bin, and then we have a solution to a complex problem. So this is proof by contradiction. So we have to prove proof by contradiction first. In other words, we have to show that proof by contradiction as a mechanism is logically sound. Okay, it makes sense. Okay. So I start with this one here. Okay, so I'm just going to skip all these steps because we're running out of time. We got about 7 minutes left. So I want to get to the tree first, and I will leave the pine needles a little bit later. So I want to prove this. If P implies Q is known to be true, then I can just arbitrarily add a third term, R, and then we say P and R as one thing also is going to imply Q or R. Okay, it actually seems to make sense just intuitively, but I can actually prove it using Boolean algebra as well. Is that okay? Now, in addition to proving this using linear algebra, Boolean algebra, what is the other way to prove this? It's a recurring theme in today's lecture. That would be proof by contradiction. I cannot prove proof by contradiction using proof by contradiction. Yes. A truth table, very good. So I can use a truth table, P, Q, or R, 3 independent variables, 8 rows, right? And then I look at this entire expression. It should be a 1 on every single row. If it's a 1 on every single row, that means the overall implication, this implication, is always true. Is that okay? All right. So why is that of any use? Well, we're going to do the following. So then we look at this here. And basically, in this case, psi is everything that is known to be true already. Okay? And phi is the theorem that you're trying to prove. Is that okay? So I'm just giving these things labels, okay? So if the theorem is in fact true, then the implication has to be true. Because that's the whole idea of a mathematical proof. You start with things that you are told or known to be true. You have a theorem that you suspect is true. But if the implication is established, then you have a proof. If psi is true, then phi has to be true. That's the whole idea of a mathematical proof. Okay. if that is the case, using this theorem that I proved a little bit earlier, don't you think I can just add a conjunction with something on both sides and that implication would still hold, right? What if I add this component that is kind of tricky? I added the negation of the theorem that we want to prove. Okay, well, that theorem doesn't say that I cannot do that, right? The theorem just says, you can add anything you want. So I decide to add not phi as the extra component. So now we have psi and not phi implying phi and not phi. Wait, phi and not phi is always going to be false. Okay, if you want to convince yourself, phi and not phi is going to be false all the time, use a truth table. Okay, so that means phi and psi and not phi has to imply 0. It has to imply a contradiction. Is that making any sense at all? Once again, what is psi? Psi is everything that we know to be true, that we are told to be true, all the axioms, okay? And then phi is actually the theorem that we want to prove. So if you negate the very theorem that you want to prove, and then you form a conjunction with everything else that is known to be true, it should guarantee to get to a contradiction. Is that okay? That is the basis of proof by contradiction. Is we are actually looking for the false. We are looking for the derivation that ends up and go like, oh, that is always false. That's a contradiction. So today we talked about, so I'm just taking a step back, so that next Monday when we come back, we kind of have all these pieces in place, and then we'll just talk about how those things are going to connect. So what we talked about today is the soundness and completeness of inferences. Okay, so that's kind of more or less a definition, not very technical. So the technical stuff involves resolution. Resolution is really cool because you start off with an expression with 3 terms, and you end up with an expression only with 2 terms. We can get rid of one of the 3 terms. That is kind of cool. And then on top of that, we talk about proof by contradiction, which is a very useful technique of proving something, and it's counterintuitive, because what you do with proof by contradiction is you start with everything that you're told to be true, okay? But then you negate the theorem that you want to prove, and then you combine that. That combination has to be false all the time, and you have to show that combination is false all the time. So those are the 2 pieces that we have talked about today. And we also talked about CNF, conjunctive normal form, which is basically just saying, give me any Boolean expression, I can re-express it in a particular way. It's a gigantic conjunction of disjunctions, and each disjunction can only contain variables and the negation of variables. So those are the pieces that are kind of still floating because there's no connection between those pieces at this point. Resolution, CNF, and proof by contradiction. So next Monday, within the first 15 minutes or so, we'll have that magical moment of, ooh, so that's how all of these things connect. But in order for that magical moment to happen, you guys will have to study over the weekend, at least cover everything up to here, because otherwise you'll miss the magical moment, because I will say something profound and go like, But if you read everything up to this point, the next step is like, whoa, that is cool. But you have to say in the Keanu Reeves way. That's the only way to say, whoa. So you guys have a nice weekend. I'll see you on Monday.